A quiet question drifts through the dark. What is dark matter? Really, we can't see it, we don't feel it, and yet the universe keeps whispering that it's there, all around us, making up the vast majority of all matter. It's the invisible architecture holding everything together. The truth is, all the stars, planets, and galaxies we can see, all the stuff we've ever known, is less than 5% of the cosmos. The rest is a profound mystery. Tonight, let's look, gently, at the clues. Our first clue comes from the graceful spin of galaxies. Think of our solar system. The outer planets, like Neptune, move much more slowly than Mercury, which is closer to the sun's immense gravity. That's how gravity works. So, we expected stars on the far edges of a galaxy to drift along slowly. But when astronomers like Vera Rubin looked, they found something astonishing. The outer stars were moving just as fast as the inner ones. It was like watching a carousel, where the horses on the outer rim kept pace with those near the center. This shouldn't be possible. The only way to explain it is if the galaxy is embedded in something else. A vast invisible halo of matter providing the extra gravitational grip needed to keep those speedy stars from flying off into the void. Our second clue is written in bent light. Einstein taught us that mass warps the fabric of spacetime, and light follows that curve. So, massive objects like galaxy clusters act as cosmic magnifying glasses. They bend the light from more distant galaxies behind them, stretching it into beautiful ghostly arcs. By measuring how much the light is bent, we can weigh the cluster, and every time the answer is the same. There is far more mass than we can account for from the stars and gas we see. This effect is seen most dramatically in the Bullet cluster. Here, two galaxy clusters have collided and passed through each other. The ordinary matter, the hot gas, smashed together and slowed down, glowing brightly in X-rays, but the gravitational lensing map shows that most of the mass didn't slow down at all. It passed right through, like a ghost. The gravity and the visible matter are in two different places. It's a smoking gun for matter that doesn't interact with light or with itself. Our third clue is the baby picture of the cosmos, the cosmic microwave background. This is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. It's incredibly uniform, but it has tiny temperature ripples. These ripples are the seeds of all future structure. When we run simulations of how the universe evolved, we can only grow those tiny seeds into the vast galaxies and clusters we see today if we include a huge amount of cold, slow-moving dark matter. Without it, the universe would be a thin, uniform soup. The match between the model and reality is beautiful. And on the largest scales, galaxies aren't scattered randomly. They form a magnificent cosmic web, immense filaments of galaxies surrounding vast empty voids. Our best simulations show that this web is a gravitational scaffold, woven by dark matter. The ordinary matter we see is just settling into the deepest parts of this invisible structure, like dew collecting on a spider's web at dawn. Many clues, all pointing to one quiet, powerful idea. So, what is it not? It's not ordinary matter, protons, neutrons, atoms, that's just dark. Not unlit stars, cold gas, or dust. We would see the effects of that much normal matter absorbing or emitting light at other wavelengths. The universe would look very different. It's not the familiar neutrinos we already know about, at least not entirely. They are incredibly light and fast-moving, zipping through the cosmos at nearly the speed of light. They are what we call hot, dark matter, and they're too flighty to clump together and form the galactic halos we observe. And while some primordial black holes might contribute, they can't be the whole story. So, what could it be? The leading candidate for decades has been the WIMP, a weakly interacting massive particle. This would be a new type of subatomic particle, heavy and slow, that feels gravity but barely whispers to normal matter. It's an elegant idea, but despite years of searching, we have found no definitive proof. Another fascinating possibility is the axion. Axions would be incredibly light, but created in such vast numbers that they could account for all the missing mass. They are less like tiny marbles, and more like a vast, oscillating field filling all of space. A cosmic hum, just below the threshold of our perception. Then there are sterile neutrinos, hypothetical cousins of the familiar neutrino. They would be even more reclusive, interacting only through gravity. They are a quiet, subtle candidate, perhaps tipping the scales in the early universe to shape the cosmos we see today. And some still wonder about primordial black holes. ancient relics from the first second of the universe. If they exist in the right size range, they could be wandering the cosmos, completely dark and incredibly hard to detect. It remains an outlier idea, but one that scientists are carefully testing. How do we search for something that doesn't want to be found? One way is to go deep underground, to escape the cosmic rays that bombard Earth's surface. There, in ultra-clean labs, scientists build detectors filled with liquid xenon, or special crystals, waiting for the faintest nudge, a single quiet tap from a passing dark matter particle, transferring a tiny bit of energy. Another way is to try and create it. At particle colliders, like the Large Hadron Collider, we smash protons together at incredible energies. If dark matter particles are produced, they would fly out of the detector without a trace. We could only infer their existence from the missing energy and momentum, a ghostly fingerprint betraying their escape. And finally, we look to the sky itself as a giant laboratory. If dark matter particles can collide and annihilate each other, they might produce a faint telltale glow of gamma rays from the centers of galaxies. Telescopes on the ground and in space are scanning the heavens for this and other subtle, gravitational clues, weaving together a net of evidence, stitch by careful stitch. Is it possible we're wrong, that there is no new particle, but that our understanding of gravity itself is incomplete? Some theories like MEON, or modified Newtonian dynamics, propose that gravity behaves differently on galactic scales. These ideas explain rotation curves well, but they struggle to explain the bullet cluster or the patterns in the cosmic microwave background. For now, across the full range of evidence, dark matter still fits best. Whether the answer arrives tomorrow or a century from now, the search itself changes us. It teaches us humility and patience. It reminds us that the universe is under no obligation to make sense to us. Tonight, as you look up at the sky, know that you are looking through an invisible ocean. Breathe in curiosity, breathe out uncertainty. We are slowly, carefully, learning to read the universe's hidden language, one gentle clue at a time. It is a privilege to live in an age of such profound questions, to be part of the generation that might just find the answer. Let your thoughts drift, vast, gentle, unhurried. For now, let the stars be calm, and let the question rest with you. The search continues with the dawn. But tonight, there is only the quiet, the mystery, and the sky.